Um, Hello everyone. Hello everyone. I guess I'm audible to you all. Can somebody like respond?
Yes, sir.
Ah, cool. Okay. So I guess wait, I'll add more people. Yeah. So you guys have already seen week zero and week one's materials, and week two lectures have already come out, right? So what we are going to do is we are since since the other PMRF TAs are going to be discussing the previous year questions or some other questions, what I'm going to do is I'll be discussing some of the concepts and then some basic problems related to that. You guys can all see the sheet, right?
Yes, sir.
Okay, yeah. So yeah, admit. Hmm. So what I'm going to do is I'm going to like start with a general trivia about robotics, like what Sir has also discussed in his lectures. So it's about the origins of the word robot, it's about the three laws of robotics, right? So, robot, the origin of this word was from a play by Karl Kapek, and the word robotics. Okay, so the word robotics was coined by Isaac Asimov, and Isaac Asimov, he's also famous for his three laws of robotics. Okay, so then these three laws were also extended to uh, four laws of robotics. So the law that was added was that the robot should not let anybody come to harm due to inaction, the humanity. Okay, so I think you guys have already learnt about the three laws. So I'll just tell you what the fourth law is. It is a robot should not let harm to humanity through action or inaction. Okay, yeah. So also there are many different kinds of robots. Okay, if we talk about types of robots, okay, then there are wheeled robots, there are aerial robots, wheeled robots, then there are aerial robots, there are underwater robots, then there are legged robots, right? So all of them have similar basic concepts that we are going to discuss in the initial weeks, but most of them have different mechanisms for actuation. Mm, many people just keep coming. Yeah, okay. So yeah, mechanism for actuation, the media in which they work in, and the type of control algorithms they use. Okay, but most of the basic concepts, like what kind of joints they use, okay, they remain same. Okay, so now uh, a robot consists of joints. Okay, why joints? Because a robot is not a single body. Okay, a robot is a multi-body system that can move. Okay, those multiple bodies can move with respect to each other. Okay, for example, if we talk about, let's say, an aerial robot, that is a drone. Okay, um, if I draw a drone like this, okay, let's say this is the frame of the drone, and these are the propellers of the drone. Then, see, this frame is body one, and every propeller, okay, it's a separate body. Body two, body three, and so on, four and five. Okay, so in total, there are five bodies here. Okay, and every propeller can rotate along its axis. Okay, so there are joints between bodies, right? Between body 1 and 2, there is a revolute joint. Okay, so now let's say we come to types of joints, right? So some of the elementary types of joint are uh, revolute, you know, prismatic, cylindrical, spherical, and like there are more, right? So these are one-dimensional joint. Okay, so they allow motion along only one axis. Okay, cylindrical joint, it's a 2D joint. Okay, it allows motion only along two axes, two orthogonal or non-orthogonal axes. Yeah, you don't need to raise your hand. You can just unmute and start asking. And spherical is a 3D joint. If somebody wants to ask something, you can ask. I think I know what you were going to ask. Yeah, this is what I was going to say. Types of joints. Okay, so um, whenever there is a 1D joint, okay, what we say is that there is 1 degree of freedom. Okay, so like every joint introduces a degree of freedom in the body. Okay, degree of freedom, it means it can freely move in that many directions or about that many axes. Okay, so every joint introduces a degree of freedom, and every constraint takes away a degree of freedom. Okay, so let's say if we want to identify how many degree of freedom uh, any body has, right? So let's say we take the example of this drone. Okay, how many DOFs does this have? Okay, so first of all, as I mentioned, degree of freedom mentions the number of independent motions a body can have, right? So since any robot is a multi-body system, we have to add up all the degree of freedom of all the bodies. Okay, so we first talk about body one. Okay. So how many degrees of freedom does body one have? Okay. Since body one can move, you know, uh, it can have translational motion, right? Because a drone can move along the x-axis, y-axis, it can move horizontally as well as vertically. Okay, so it can have three translational axis or translational motion, and then it can have three rotational motion. Okay, let's say we call that phi theta psi, right? Because a general rotation in a 3D space can be represented by three parameters, three independent parameters. Okay, so we can see that for the motion of only the base, okay, for the motion of only the base, six parameters are required. Okay, so the base has 6 degrees of freedom, but is that the total degrees of freedom of the robot? No. Why? Because there are other bodies as well, the propellers, right? Yeah, so now these six are for body one. Okay, that is our frame. And every propeller can rotate about only one axis with respect to body one. Yeah, sure. You can ask Setu. Um, yeah, hello, Setu. If you want to ask, you can ask or you can lower your hand. Okay, you can ask when you feel like that. Yeah, since every propeller, can rotate about only one axis. Okay, if there was no joint between the propeller and the body, then the propeller also would have 6 degrees of freedom. Okay, but because there is a constraint, okay, there is a constraint due to both of these bodies being attached, 5 degrees of freedoms have been restrained. Okay, because the propeller cannot move independent of the body, right? So it cannot have independent translational degree of freedom. Okay, and also it cannot rotate along the other two axes. Okay, so all the propellers, okay, they only have 1 degree of freedom since it's a revolute joint. Okay, so in total, okay, so for a quadcopter, quadcopter is the one with four propellers. So total DFs are 6 plus 4 for each propeller. Okay, so 10 DFs. So this is basically how you can, identify the number of degrees of freedom of body. Okay, why do we identify number of degrees of freedom? Because this helps us to uh, identify the size of the generalized coordinate vector required to represent the system equations. Okay, so if I want to write the equation of motion of this system, then what are the number of variables? Okay, what is the least number of variables that I need to consider to, you know, completely represent the system? Okay, so this is the least number of variables. There can be more. Okay, that is a redundant representation, but there cannot be less than this. Okay, let us take one more example. Okay, let's
Sir,
say, yeah,
can you just show the drone? So the base of the drone, sir.
yeah,
Uh, like we have written it as six, no, sir.
yes,
Base of the
hmm
degrees of freedom.
hmm
Uh, so the base on its own cannot rotate, no, sir. Like only when the it is the propellers that make the base to rotate, no, sir. So how can we write three degrees of freedom for, like, how can we tell that the base has 3 degrees of freedom from rotation?
See,
Like
you're confusing two things. Uh,
yes,
the base rotates because of the forces generated due to propeller, right?
yes, sir. Yes, sir. Yes,
Right.
sir.
But the base can be oriented in in any direction, right? In
Yes,
3D,
sir.
right?
Yes, sir.
So you
Yes.
first have to look at the base itself. Okay, since it can move in 3D in three directions and then it can rotate in 3D in three directions. That is why it has 6 degrees of freedom, the base of the propeller, the base of the drone. Okay, now
Okay.
for
Mm,
every translation or orientation, irrespective of wherever the drone is, the propellers can rotate with any speed, right? The propellers
mm,
basically can have any position along that particular axis, right?
mm. Yes, sir.
So that
Uh,
adds one additional degree of freedom.
okay. Sir, so we decide degrees of freedom based on not the, like, based on the ability of that body to move or not. Like here the base is generally at rest. It is due to the, like you said, it is due to the forces that makes the base to rotate. So
Yeah, because
even
see,
if the
if you have seen the equations of a drone, okay, they consider it only to be a 6 degree of freedom system, right? But there, what
okay.
they do is
Hmm,
they take only the base, okay, and then they replace the propellers with the external forces,
okay.
right? Now, again, there are no bodies, right? So, of course,
Hmm,
you do not count the degree of freedom of in this kind of representation, okay, because here now there are no propellers, there are just forces that can vary. Okay, F1, F2,
hmm,
F3, and F4. So in this case, you call it a 6 degree of freedom system. That yes. So this six are X, Y, Z of base and the orientation. But if you consider propellers as well,
hmm,
okay, in that case,
hmm.
it has to be 10.
Okay, sir. So no matter, like we said, take it as degrees of freedom if the body has ability to move.
Yes.
Whether it moves or on its own or not, that is not, even those two comes under. Uh, Even then, we just tell the degrees of freedom, right?
Yeah. So
If it has
see,
the ability to move, then we
yes, a
say
body can
then
have the
we say
ability
10.
to move in, let's say, in this case, six independent directions, but in reality, it might not be able to move, you know, in all of them independently because, let's say, we talk about the quadcopter, it cannot, move in X without pitching, right? So this
Hmm.
X and pitch, okay, if I say that these are the Euler angles, so the X and pitch are coupled, right?
Okay. Yes, sir.
Okay, so
Yes, sir.
yeah, so in those some of those degrees of freedoms can be coupled. Okay,
Okay.
but
Okay.
it can still
Okay.
perform that motion, right?
Yes, sir. Yes, sir. Okay.
Yeah.
Yes, sir. Got
So
it.
again,
Got
like the number of actuation you have does not need to be equal to the number of independent degree of freedoms, right? But if you have lesser actuations, then of course there will be some mixing in the system. Okay, because if let's say you write the system equations like this. Okay. So now this B matrix, okay, first of all, this A matrix can have some cross terms. Okay, and this B matrix, if X is 6 cross 1, you can be, let's say, 4 cross 1. Okay, it does not need to be 6. Okay, and but since it is 4, and since this system is 6 cross 1, okay, so this B matrix will be 6 cross 4, and it can have some cross terms, let's say, for uh, here, let's say, again, it can have anything, let's say 2, 2, 0, 1, 0, 1, okay, something like this. So yeah, uh,
Yes, sir.
multiple degree systems can be coupled through actuation because it is under actuated system. Cool.
Yes, sir.
Okay.
Yes, sir.
Yeah. So I'll just take another example. Okay, of a very simple 2R robot. Okay. So a 2R robot is a two-link robot that has two revolute joints. Okay. So again, as I mentioned, that the any robot is a multi-body system. Okay. So this also you have to identify all the bodies in the system. So the first body that we have here is the ground. Okay, because that is also a part of the entire mechanism. If the ground is not there, the whole arm will be floating in space. Okay, so you have the ground, and then you have, you know, we call it link one, and then link two. Okay, and it's a planar mechanism. Okay, it cannot move out of the plane of the paper. Okay, now let's say we want to write, the total degree of freedom of this robot. So for body one, now it's a 0 degree of freedom. Why? Because it's ground. It cannot move. It is rigidly attached to the inertial frame. Okay. For link one, okay. Now, if link one was separated, okay, from all this, but it was constrained to move in the plane of the paper. Okay. So then it would be a planar joint. In that case, it would have 3 degrees of freedom. But this planar motion has been constrained due to this joint with the ground. Okay, so now it can only rotate about this point. It cannot translate, you know, uh, to anywhere other than this point. So this has 1 degree of freedom. And similarly, link 2 with respect to link 1. Okay, let's say it moves by an angle theta 1. Link 2 with respect to link 1 can only rotate. It cannot move anywhere. Okay, so that also has only 1 degree of freedom. Why? Because 2 degrees of freedoms have been arrested due to the joint. Okay, due to the constraint imposed by the joint. Okay, so the total DF for the system, okay, for this it is 2 DF. We knew it, but we just try to go, come at it through the concepts that we already know. Now, in the lectures or in some books or in your previous courses, you might have come across some formula, right? To identify the degrees of freedom of a system. Okay, so those formulas, they are basically, you know, a mathematical expression for what we are doing here. Okay, so again, if you want to derive at that formula, you just need to remember that the total number of degree of freedom is the total individual degrees of freedom of the body minus the, degrees of freedoms arrested due to the constraint posed by the joints. Okay, so you do this or you come at it through that formula. Both are same things because that formula is derived based on this logic. So I think I'll just, you know, uh, move towards another concept that is of the work volume. Okay, so what is work volume? Okay, so work volume is basically the volume of the workspace of the robot. Okay, now again, there is one more term that we need to explain. What is the workspace of a robot? Okay, what is a workspace? So, workspace of the robot is basically all the points of the desired point on the robot where it can go. Okay, I'll just you know show it with the example of a two-link manipulator as above. So let's say this point, okay, this point on the end effector, okay, I call it P. This is my point of interest. Okay, so now for all valid values, okay, of theta 1 and theta 2. Why theta 1 and theta 2? Okay, because as I said, it's a 2DAF system. So the complete robot, the configuration of the robot can be defined uniquely if I uniquely define theta 1 and theta 2. Okay, so for any given theta 1 and theta 2, we will have a position of the point P. Okay, let's say this is length L1, this is length L2. Okay, so for all possible values of theta 1 and theta 2, sorry, so for all possible values of theta 1 and theta 2, the resulting uh, you know points or the resulting values of the point P, okay, they are the workspace of this robot basically. Okay, so if L1 and L2 are equal, okay, let's say, so what will be, so the workspace will look somewhat like this. Okay, if you know theta 1 goes from minus pi to pi, and theta 2 as well goes from minus pi to pi. Okay, so then it can have different ranges. Okay, if L1 and L2 are equal, then it will be something like this. Okay, something like this, I mean, these portions, this is the num basically the set of points where the point P can actually lie. It cannot lie within these. Okay, if L1 and L2 are equal, if L1 and L2 are unequal, the ratio of these circles changes. Okay, so this is basically the workspace of the robot, and the volume of the workspace is the work volume of the robot. Okay, and knowing work volume is important to, let's say, define safety. That yeah, uh, near the robot, this much volume should be kept free to move so that there are no accidents. The work volume is useful to define if you want to define that yes, if a particular object is within the reach of the robot or not. Okay, so all those concepts are like based on the workspace and the work volume. Okay, so a workspace is like a more basic, more important concept than a work volume, and it is used like very frequently. Okay, I think I'll just come now to the you know concept of position and orientation. Okay, so in the above example, we said that the point P, okay, is our point of interest. So point of interest, we wanted to know the position of P. Okay, so in this example, if I attach a coordinate frame at the ground and I say this is X and this is Y, so the coordinates of P were L1 cos theta 1 plus L2 cos theta 1 plus theta 2 and L2 L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Anybody has any issues in how I got these coordinates? I will assume no, and then I'll keep moving forward. If anybody has, they can just speak up. Okay, so this is the position of the point P in this 2D plane. Okay, so uh, okay, what is the position? It is the translational displacement with respect to origin. Okay, now with respect to origin of what? Alright, so again, the point P had these coordinates only when I took my coordinate system, positioned at this particular position. If my coordinate system was here, right, then the position would be different because then this vector would also be added. Okay, so before we talk about position and orientation, what we need to talk about is reference frames or coordinate frames, right? So what is a coordinate frame? A coordinate frame is basically for 3D a set of three uh, independent, in many cases mutually perpendicular set of axes that we will denote by E1, E2 and E3 along with a common origin called O. Okay, so now this combination of the origin and these three unit vectors that I will call basis vectors. Okay, this is what is a frame. Okay, so this is how I will represent a frame, right? With curly symbols. So when I said that I will attach a frame here, okay, so what I did was I decided on an origin and then I decided on two basis vectors in a 2D plane. That is why I only chose two basis vectors. If it was in 3D, I would have to choose three basis vectors and an origin. Okay, so now when we talk about the position of any object, it is about the chosen reference or chosen coordinate frame. Okay, and these coordinate frames, the origin can be anywhere. It is upon us where we choose to place them or based on the problem. Sometimes you just have to choose some coordinate frames uh, for simplicity or for taking into consideration the alignment of the body. Different reasons. We'll come on to those, you know, in further lectures. Okay, so let's say if there is this point P, okay, and I want to define the position. So I can define the position of this point P with respect to this frame. Okay, so if let's say the vector uh, for P I call R P uh, with respect to O, right? This is RPO. Hmm? So so this is currently a vector. Okay, I will denote vectors by putting a little bar under them, right? and I will denote unit vectors by putting a little hat over them. So this vector right now, okay, like since we have studied that vectors are independent quantities, they do not depend on the reference frame, right? Because they can freely float in space. But when we want to write coordinates of a vector, okay, then we need to assign a coordinate frame. Okay, so this is how we'll represent the coordinates of a vector. Okay, so if we go to the uppercase, this is how we would properly write. If let's say we say that this is the E frame, okay, so in the E frame, the coordinates are, if I'll just write it again. So C1 I will write for cos theta and C12 I will write for cos theta 1 plus theta 2. Uh, okay, yeah, I can. And similarly, S1 is for sin theta 1 and S12 is for sin theta 1 plus theta 2. Okay, now if we were talking in 3D and we had three basis vectors, then uh, there would be three coordinates. Okay, so what are I I should just just briefly comment on what are actually the coordinates. So we know that any vector in 3D space, I should start on the other page. Okay, so any vector v in 3D space can be written as a linear combination of three independent vectors. Okay, they do not need to be perpendicular or orthogonal, but they need to be independent, linearly independent, right? So uh, these coefficients of these independent vectors, okay, if I choose these, three to be my basis vectors, then these coefficients are what we call the coordinates of a vector. Okay, now we can see that if we keep the vector same, okay, but we change the, okay, so these are u1, u2, and u3. We can change the basis vectors, okay, but the vector will not change. Okay, so if I change the basis vectors, the coordinates will change. Okay, because the proportion in which I have to, add them to get to the to achieve v vector will be different, right? So these basis vectors are uh, in our case e1, e2, e3, and the coordinates represent, you know, how much of e1. Okay, what is the scaling of e1 and what is the scaling of e2 and the scaling of e3. Okay, uh, these coefficients determine the scaling of basis vectors, and then we just add them up using a simple vector addition to get our vector v. Okay, so I think we have talked enough about the position, and what is important is we talk about orientation of a body. Okay, so whenever we say orientation of a body, we actually mean the orientation of the frame attached to the body. Okay, because for let's say any general body, I can attach a frame at its center of mass, right? I call the center of mass by B. Okay, and these coordinate vectors, let's say I call them E1 prime, E2 prime, and E3 prime. You can notice I'm not calling them X, Y, or Z, right? That is the usual convention that we use. You can use X, Y, or Z also. X1, Y1, Z1, XB, YB, ZB, whatever you want to use it. I use E1, E2, E3. Okay. And I will now say that there is an inertial frame, okay, or the base frame or the world frame with origin O with basis vectors E1, E2, E3. Okay, so now the position of any body is defined as you know, this displacement vector between the origin of the two frames. Okay, which two frames? The world frame and the frame rigidly attached to the body. Okay, when we say rigidly attached, it means the frame will always move with the body and the frame will orient with the body. Okay, so the frame will move with the body and the frame will orient itself with the body. The frame cannot move without the body moving, basically. So this is the position. Okay, now for the orientation. Okay, what is orientation? Basically, we want to get the relative or the orientation or the mismatch between the basis vectors, you know, between the two frames. Let's call this frame E and let's call this frame EB. Okay, let's define them first. Okay, so what is E? This is O, E1, E2, E3. And let's define EB. It is B, origin at B, E1 prime, E2 prime, and E3 prime. Okay, so what is orientation? Mismatch between basis vectors of E and EB. Okay, in this particular case, E and EB. And how do we define that mismatch? Uh, so there are multiple ways to define it. So the first and the most simple way is the direction cosine matrix that we all have heard about, right? So what the direction cosine matrix does is, okay, so it just takes dot products of all these three vectors, okay, in different combinations, right? So let's say we want to write E1 prime, E2 dot E1 prime, E3 dot E1 prime, and we just, you know, we keep going on like this, E3 dot E3 prime. So this is the direction cosine matrix. Okay, that so the entries of this matrix, I like there will be three more entries. I've just not written them. So the components of this matrix, they represent the mismatch between the basis vectors between these two frames. Okay, so this is one way to represent the relative orientation between two bodies. Okay, and if they were the same, okay, if let's say both the frames were overlapping each other, there was no relative orientation, then this would just be an identity matrix. Okay. The other way is a rotation matrix. Okay. So a rotation matrix is basically if the a vector, let's say A, had its components represented in frame B. Okay. How would the components of the same vector look like in frame, in the original E frame. Okay. So what we say is that the components that are in EB frame, okay, let's write EB here. Okay, they can be multiplied with a rotation matrix to get these components. Okay, and a general, if you follow, the general convention that people use in dynamics, then the relation between the direction cosine matrix that we here represent using capital A, and the rotation matrix is basically this. Okay, so or you can say R equal to A transpose, but it again depends on the convention that you choose. That I think Sir will also touch on more in the coming lectures. Okay, now I just want to talk about rotation matrices again for a bit. Why do I want to talk about them? Because they are used everywhere in robotics. Okay, they are used the most in robotics. Okay, so again, we saw rotation matrices. They help us represent the relative orientation between two bodies. Okay, but any 3 cross 3 matrix in a 3D space, it will be a 3 cross 3 matrix, right? Because the A matrix was also a 3 cross 3 matrix, right? Here, this is a 3 cross 3 matrix, and since both of these have three components, they are 3 cross 1 vectors. So this transformation, the linear transformation matrix that we are using, should also be a 3 cross 3 matrix. Okay, that much is clear. So, if we say that the matrix R, okay, so I'll just comment on R a bit. R is a tensor that is represented using a matrix, using a 2D matrix. Okay, so R is not just a matrix. R is a tensor that we apply, that we combine with other tensors like vectors. Okay, but when we want to program them or we want to work with them numerically, we represent them, you know, using matrices and vectors. Just keep that in mind. Okay, so if we just say that R is any, 3 cross 3 matrix, so this is how we write the set of all 3 cross 3 matrices, real with real entries. Okay, so this is wrong. Okay, any 3 cross 3 matrix cannot be a rotation matrix. Okay, why? Because a rotation has to preserve the length of the vector that it is rotating. Okay, it cannot scale the length. Okay, so what happens is this R matrix, okay, belongs to a special group that we call SO3. Okay, and what is SO3? It is the special orthogonal group. Okay, why orthogonal? Because it comes from the orthogonal matrix. Okay, so R is basically your orthogonal matrix where R inverse is just R transpose. Okay, So this is one of the identities that R has to follow. And for any orthogonal matrix, the determinant can be plus or minus 1. But we choose R such that the determinant is always plus 1. Okay, and how does it, depend if it will be plus or minus 1? If you choose right-handed coordinate system, right? If you choose right-handed coordinate system and then you write your R matrix, then it will always have a determinant of plus 1. If you choose left-handed coordinate systems and then write the rotation matrix, then the determinant will be minus 1. Okay, so it's a good check to you know be sure that yeah, the coordinate system that you're working with is right-handed. Okay, because everybody uses a right-handed coordinate system. Okay, so this plus 1, okay, this restriction for it to be only plus 1, not minus 1, is why we call it a spatial orthogonal group. Okay, and this that the inverse is its transpose is what leads us to call it an orthogonal matrix. Okay, so any rotation matrix is a part of this SO3 group. Okay, so this SO3 group has these two properties, that the inverse is the transpose of itself and the determinant of R is plus 1. Now, if you want to talk about group itself, okay, so a group is a mathematical concept, then we can even approach the rotation matrices from there. Okay, um, so let's do that because that will be good for us. Okay, so let's talk about the rotation matrix group, or in this case, I will talk about the SO3 group. Okay, so what is a group? A group is a collection of a set. Okay, in this case, a set of rotation matrices and an operator. Okay, a group is a collection of a set of numbers and an operator that follows four rules. Okay, first is called the group closure or just closure. Okay, that for all R1 and R2 that are sampled from this group. Okay, and if we perform this action on R1 and R2 leading to R, this R should also be in the same group. Okay, so this is one of the properties of the group that the rotation matrix is also for. Okay, what I will do is, see, this call might end in 7 minutes, so I will just make a new link and share it with you guys over the chat right now. Okay, so that if this meeting abruptly closes, you can just join that new link. So just give me 1 minute for that. Yeah. Hmm. So just copy this meeting link. If this meeting ends abruptly, then we will just, move on to the link that I just provided. Uh, yeah. Okay, so the first one is the closure. Okay, I'll just move on. I just push these things some a bit fast. Okay, so the second thing is the existence of an inverse element. Okay, so this inverse element should also be in the SO3 group. Okay, and how do we define an inverse element? To define inverse element, we first have to define the identity. Okay, so the identity is basically if there is an R that is from that group, okay, and we say that the identity is represented by I, then R operated with that identity is just R again, and it does not matter which side this I acts on. Okay, so this order only in the case of identity is not important. Okay, and then we talk about inverse. So R times R inverse, where both are in the group, is an identity. Okay, and in this case, R inverse is just R transpose. Uh, do you guys have any problem till now understanding this thing specifically? You can just say yes or no. Anyone? Okay, so there is one more um, property of the group that is left, and that is, so yeah, like we have the closure, we have the inverse, we have the identity, and I think there is some fourth one also. I can't remember it right now. So one important thing to remember is this group is not commutative. Okay, what we mean is that R1 operated on R2 is not the same as R2 operated on R1. Yeah, somebody raised their hands. They can just unmute and speak. Pawan? Okay. Yeah, like you have to keep this in mind. Okay, if any group that is commutative is called it's a special group. Okay, it has a different name. It is called an abelian group. The group of rotation matrices is not in an abelian group. Okay, so like this is just about the mathematics of rotation matrix. What you need to keep in mind is the inverse is just the transpose and the determinant is plus one. Okay, and you can just look up this fourth property of the group as well. That rotation matrix is also called. Okay, so you can just verify this on your own. Just a good exercise. Okay, so we saw two ways to represent orientation. Okay, what were these two ways? First was the direction cosine matrix that we have been learning about since our ninth grades. The other one is rotation matrix. And the other one is rotation matrix. There are other representation of orientation as well called Euler angles. Okay, and Euler angles specifically, like there are 12 different kinds of Euler angles. Okay, there are 12 variations. There are fixed angles. Okay, there are quaternions. There are there is the axis angle representation. Okay, I think we'll just wait for 5 minutes so that others can also come. Yeah, we can do that. Okay, so what we started with was just like general trivia about the robotics. Some things that people, just know for fun about robotics. So first is like the origins of the word robot, as sir mentioned in the lectures. It came from, a play by Karl Kippach, and the word robot was initially meant for forced labor, uh, and that is we actually use it to do. We use it for forced labor or where it is like really difficult for humans to work. That is the ideal condition of a robot. Okay. And then we talked about the word robotics. Okay, so it was coined by Isaac Asimov. Okay, he's the same Isaac Asimov who gave three laws of robotics. That was then extended to four laws of robotics. So what was the fourth law? Fourth law was robot should not harm or let humanity be harmed through action or inaction. Okay, so like yeah, there is some modification that is needed but in what I've written here, but yeah. This was done after, it was not given by Isaac Asimov, it was just added to those three laws after. So it's sometimes called the zeroth law of robotics as well, uh, instead of fourth law, because it is much more basic than the first three. Then we discussed about types of robots. There are wheeled robots, aerial robots, underwater robots, and legged robots. So all these different robots have different environments that they interact with, different ways in which they interact with the particular environment, but they have, some same basic concepts that we build upon to analyze these kind of systems. So, what are those kind of concepts? Concepts like degrees of freedom of a robot, how many degrees of freedom it has, what kind of joint the robot has, what number of bodies the robot have, all these things. So, one thing that we'll assume is that every body that we talk about is a rigid body. Okay. In this course, I don't think we'll talk about soft robots or the robots that can deform. Okay, the bodies cannot deform in our case. Okay, moving on to that, a robot is a collection of such rigid bodies. Okay, so it is a multi-body system, as we call it. Okay, so then we just took an example of a drone that was a collection of five bodies, one the frame and four the propellers. And if we, you know, uh, have to talk about the degrees of freedom of a multi-body system, then we have to talk about the joints. of that multi-body system. Okay, how are the different bodies connected to each other? Okay, so then we just discussed some of the basic type of joints: revolute, prismatic, cylindrical, planar, spherical, etc. So they are like they are different. Either they allow motion in one direction or along one direction, or into or along two directions. So when I say in two directions, like it should be implied that I'm talking about translation, but along two directions is like a much better terminology. Okay. Then I just took an example of how to determine the degrees of freedom of a quadcopter if we are considering the propellers as well, and if we just take the general, representation of a quadruped, of a quad rotor robot, where we do not consider the propellers, but we just consider the forces generated by them, then, degrees of freedom are different in both of these cases. Okay. Then we just took an example of a two-hour manipulator, how we, decided on the total degrees of freedom of that. So again, we identify the individual rigid bodies. Okay, so there were three bodies in this: ground, link one, link two, and then we started writing the degrees of freedom of every individual joint. You guys can see this, right? You can pin this video. Okay, so this is another one, so that it becomes bigger. Okay, so yeah, again, the ground has 0 degree of freedom, and then the link one in the 2D plane, okay, it could have three. Okay, for example, if this is link one, it can move in X, Y, or it can rotate. So it could have three, but since it is attached to the ground using a revolute joint, the translation degree of freedom is lost. Only the rotation is left. Okay, about this point. So it only has 1 degree of freedom left. Same is the case with link 2, that is joined through a revolute joint to link 1. Okay, so the total degree of freedom of the bodies, considering all the joints in this particular system, is 2. Okay, so then I think we started our discussion on position, right? Yeah, this is not the correct one. Okay, then we just talked about position. How do we represent position? Um, and also to represent position or orientation, we started our discussion on basis vector. Okay, how every vector can be written as a linear combination of three linearly independent vectors. But those bases, those vectors can be different. They just need to be linearly independent. Okay, so this is how we work with our basis vectors as well. And then we went on to represent orientation. To define orientation, we just defined how we will represent reference frames attached to bodies. So one reference frame that we call the inertial reference frame is always attached to the ground. Okay, it is like not moving, it is inertial. And the other reference frame, okay, it will be attached to the bodies of interest. Okay, every body will have its own reference frame, and it's called a body fixed coordinate system, BFCS, if you will. Okay, and then we define the orientation to be mismatch between basis vectors of the two frames of you know, the inertial frame and the body frame. Okay, so the mismatch between them is the orientation, and how do we represent this mismatch is what we were discussing right now. Is that we represent it using either the direction cosine matrix, either the rotation matrix, right, or the Euler angles, fixed angles. So there are different representations of orientation, but they are all interchangeable between themselves, right? You can, if you have direction cosine matrix, you can, write rotation matrix, or you can write any type of Euler angle, or you can write, anything from here. Okay, so all these are interchangeable. Why? Because they are the representation of the same orientation. Right? Orientation is the same. It is just how you choose to represent it. So I think I'll just continue. So to just briefly mention about the axis angle, we have to talk about the Euler's theorem. Okay. So what Euler's theorem says is that any orientation or any rotation can be represented by a single rotation about one axis in the 3D space. Okay. So if let's say we say that one frame is like this and another frame, okay, it is like oriented in some way. Okay, so this is our E1, E2, E3, and this is our E1 prime, E2 prime, E3 prime. Okay, so our E is origin, E1, E2, E3, and our EB is at the same origin but with E1 prime, E2 prime, and E3 prime. Okay, so what Euler theorized was that this mismatch, okay, or this transformation from frame E to frame EB can be done by rotation of the frame E about one axis. Okay, so basically you just um, fix that axis and then you rotate the frame about it. Okay, you rotate everything about it and then you'll just get your rotated frame. Okay, so that was Euler's theorem. And this axis, particular axis called n, and the angle that we rotate about this axis is basically the axis angle rotation notation. Okay, now this axis angle can be converted to rotation matrix, to quaternions, to Euler angles. You know, again, since these are interchangeable, that is all possible. These are all two-way. So I think we've talked enough about orientations. If you have doubts, you can just ask. I will like discuss more about them. But you just have to know these things when you're reading a book. Okay. So apart from the lectures that sir is taking, you must take up a book and read as much as you can if you want to learn robotics, of course. Read as much as you can about all these different terminologies that I'm giving you here, right? A coordinate frame, a body fixed coordinate system, orientation, rotation matrix, direction cosine matrix, everything. You just read, try to understand, and what you do not understand, you ask either me or other TAs in these kind of live sessions, or you just ask on the forums to sir. Okay, but ask. Okay, so now what we will do is we'll just briefly derive, right, the fundamental rotation matrices, and that will, I think, clear some of the doubts as well related to the usage of rotation matrix. Okay, so we will just do it in a 2D space for now. Okay, it means that Z is coming out of the plane. Okay, now I'm using X, Y, and Z for like just easier notation. This is the origin O, and let's say this is the point A, right? It is at an angle θ1 and has a length R, right? Now we say that it has been rotated, right, by some angle theta. Okay, the same length R, but the new position is A prime. Okay, now you see we are talking about a different vector A here, but this A could easily have been our even vector. Okay, so we could have just rotated the even vector to get, let's say, even prime. Okay, now how do we do that? So in this particular case, if this A vector was written by, let's say, x1, y1, and the A prime, the new coordinates, the rotated coordinates are x2, y2. Okay, so what we write is that x2, y2 and x1, y1. Okay, how are they related? They are related by this rotation matrix, right? This, I think you might have done this in your 9th or 10th class as well, or you can just, try to do it through geometry. Okay, just try to get the coordinates of this particular vector, right? So, yeah, like this matrix right here that you will get is the rotation matrix for the 2D case. Okay, and if you extend it to 3D, it is the rotation about Z. S theta, S theta, E theta, 0, 0, 1, 0, 0. Okay, so this is the fundamental rotation matrix about the Z axis. And similarly, if we write for X and Y, okay, it is 1 because if you are rotating about X, the X does not change, only the Y and Z will change. C theta minus S theta, S theta, C theta. And all these, derivations you can do in a similar way. Okay, just write the basis here. Let's say X and Y, you can write Y and Z or X and Z to get rotation about Z and Y respectively, Z and X. This is C theta, 0, theta. Okay, so these matrices are called the fundamental rotation matrices. Okay, and these are then combined to get the final rotation matrix by using a concept or the orientation represent called the Euler angles. So what Euler angles are? Euler angles are basically like in Euler's theorem. Okay, we said that to go from one frame to the other, you just rotate about one axis that can be oriented anywhere. Okay, what Euler angles are is basically you keep rotating about these basis vectors of the new frame successively 3 times. Okay, so let's say to go from EB, no, from E to EB, I could rotate first about X, then I could rotate about Y, then I can again rotate about X, by some angle. Okay, so all these are different angles. Okay, rotate about X, Y, or I can even rotate about Z in the end. Okay, so the angles that I end up with will be different in both of these cases. Okay, and these are two of the 12 cases of Euler angles. These are the X, Y, X Euler angles. These are the X, Y, Z Euler angles. Okay, so once you write it this way, and once you multiply them, you will get the final rotation matrix R that will, represent your orientation of body with respect to the world. Now, we have talked about translation in isolation. We have talked about orientation, independently. But what happens when both of these are happening simultaneously? Okay, so in that case, we call that combined transformation as homogeneous transformation. Basically, when we are translating and rotating a point or a vector or a coordinate frame together. Okay, it's not like we are just orienting them or we are just transforming them. We are doing both of them together. Okay, so as always, we'll do everything with respect to the world frame. And we'll bring back our notation of E1, E2, and E3. And let's say a frame was initially here. Okay, a frame with basis vectors E1 prime, E2 prime, E3 prime, and origin B. Okay, so O and B were at same place initially, but then this vector or this frame, it was translated by this much and it was rotated as well. And this rotation is represented by R, B, W, and the translation by R, B, O. Okay, so what you could do is uh, you can represent this complete transformation by a single matrix rather than having two different, you know, uh, tensors here. You just combine them into one, like this. So it's a 4 cross 4 matrix where the initial 3 cross 3 block is the rotation matrix. The 1 cross 3 row vector right below the rotation matrix is zeros in this particular case, but it can be non-zero if you take into account the perspective. So this concept comes into computer graphics. You can look up that as well. This is 1 in our case, but it is again non-zero in computer graphics if you zoom in or zoom out. And this 3 cross 1 vector is the RBO. So this is a scalar here. It's a 1 cross 1. Okay, so this is what we call the homogeneous transformation matrix. And why we do this is because, let's say there is a vector R1, right? We rotate it and we translate it by R2 to get R1 prime. Okay. Now let's say we want to rotate and transform R1 prime as well to get R1 double prime. Okay. So we rotate R1 prime this time and then we add, let's say R2 prime, right? And this is again R1, R2. Okay. If we, you know, try doing this more times, then what you'll see is you'll end up with a very dirty looking equation. Okay, because if you write everything, in terms of the original vectors now, it will be R2, R1, this plus R2 prime. Okay, so like you have to add, and multiply these different terms, okay, separately. But what you can do is you can just append, modify R1 like this. Okay, you just write the 3 cross 1 vector and then write a 1 at the end to get a 4 cross 1 vector. Okay, to let's say get R1T. Let's just call it R1T. Okay, so you just multiply this by this homogeneous matrix representation that we discussed above, and what you will get is R1 prime 1. Okay, so now there is only just one matrix vector multiplication that needs to be done. Okay, you don't need to like multiply two matrices just or multiply and add, right? And to get R1 double prime, what you need to do is just multiply another matrix to the resulting vector. And the primary advantage of this representation is that you can just multiply these matrices to get the transformation from the initial vector to the final vector. Okay, you don't need to uh, do this. Okay, like in calculate every individual term and then add them up. You can just multiply these matrices first and then just store it as a single matrix and use that for any vectors from, let's say, frame 1 to frame n. Okay, so this I think Sir has also discussed and we just touched it upon again, touched upon it. So I think the only thing that is remaining is the DH parameters, but I think you guys need some more time to think about DH parameters. I will just, very briefly explain what DH parameters are maybe. So, like, it is just a convention that is used, okay? So, it's the DH convention, as we call it. Okay, so what I'm making here is basically what I'm trying to make here is a multi-link robot. Okay, so this here is a revolute joint. Okay, what I will make here is also a revolute joint. Okay, so these are like multiple links. Okay, so let's say this is link I minus 1. This is link I. This is also a joint. Okay, and this is link I plus 1. Okay, and this is like joint I, and this is joint I minus 1. Okay, so again, as we said, at every body we attach a rigid frame. Okay, but how do we attach that rigid frame? That basically is defined by the DH convention. Okay, and how do we decide that? Well, first of all, we attach the Z of the body to, we align the Z with the joint axis. Okay, so the frame I will be between um, link I minus 1 and link I. Okay, and then frame I plus 1 will be between I and I plus 1. Okay, so this is Z I plus 1. Okay, so we decide Z using the joint axes. We define X of these, okay, by drawing the common normal to both these axes. Okay, since these are non-intersecting axes, both the joints, we just define a common normal, and the unit vector along this common normal for from joint I minus 1 to I, we call it xi. Okay, and similarly from joint I to I plus 1, we will call it xi plus 1. Okay, and how do you get the third vector? Since we are using the right-handed coordinate system, you just take a cross product. Okay, so your z cross x will give you y, right? So for this particular case, yi will be in these directions. Okay, so this is the DH convention basically. Like there is not much about it. Now the DH parameters that we talk about are basically the displacement between these two joints. Okay, that is called the link length parameter, AI. Okay, and then the distance between the origin of these two frames, that is called the link offset or the DI, and the angle. Okay, so well, A is distance between ZI and ZI plus 1 along XI, right? DI, distance between XI and XI plus 1 along ZI plus 1. Okay, and theta I, angle between XI and XI plus 1 along ZI, and then alpha I, the link twist, is the angle between ZI plus 1 along XI. Okay, so like this is one of the DH convention that is used that I just wrote here. Okay, like it is the convention that is used in JJ Craig, but a different convention. Uh, by convention, I mean the choice of these indices, right? That I is between I minus 1 and I, or the frame I is between I and I plus 1. Okay, so these kind of choices are um, unique to some of the authors. For example, Schilling, Fundamentals of Robotics by Schilling uses a different convention. You're free to use any of those, but it is a recommendation to just be consistent once you choose a convention, right? And I think you can then make parameter table to just make it easy to see it. If we take an example of, let's say, a 2R manipulator, right? Let's say this is length L1, this is length L2. So what we do is we start with our ground frame x0 y0. Okay, theta 1, this is theta 2. So the rotation axis or the joint axes are out of this plane in both these cases. Hmm? And we call this link 0. This is link 1, this is link 2, right? This is link 2. So we define joint 1, okay, or the frame 1 here between link 0 and link 1. Okay, so the Z coincides with Z0, Z1 coincides with Z0, and X. So similarly, then Z2 will be between link 1 and link 2, right? And X1 will be going from Z1 to Z2. Okay, so this is X1. And similarly for X2, we can define a dummy joint here at the end effector that is aligned with frame 2 always, right? And then X2 is from Z2 to Z3. Okay, and then again, we know Y is Z cross X. Okay, so the Y0 is here and Y1 will be this. Similarly, Y2 will be like this. Okay, if we try to make a pH parameter table according to these parameters that we have defined above. Okay, let's say for link 0, link 1 and link 2, we do this. Okay, we might even do this. So for link 0, everything is 0, right? Because AI distance between Zi and Zi plus 1, right? So it means the distance between Z0 and Z1, that is 0 because they coincide. Bi is the link offset. Okay, in this case it would have been the it would have been the vertical distance between the both these, but they are at the same place. But di is also 0. Okay, now there is theta I, right? So theta I in this case is, we say theta 1 and alpha is 0. Okay, then this is L1 0 and then theta 2 0, then L2 and all this. Okay, so again, this table will change if you change the convention. Okay, if you, let's say, use a different convention, you might, end up with a table like this. L1 0 theta 1 0, L2 0 theta 2 0, right? But again, that is a different convention, and then all these are there, right? We do not use this, we are using this, right? So we first rotate by theta 1, then we translate by L1, and then we rotate by theta 2, and then we translate by L2. You can just, think about that. Link 0, link 1, link 2. So again, based on the convention that sir has taught in class, you should attempt the assignments. If it is similar to this, well and good, but you should check if it is similar or not. Okay, so I think I'll end this session here. If you guys have any questions, you can ask, or you can just leave the meeting now. Tamanjeet? Yeah, thanks.